We've been thinking about Newton's first law, and it tells us that an object in motion tends to stay in motion. But come to think of it, that sounds kind of crazy, because if you actually watch things around you, objects in motion usually stop. You throw a ball, it comes to rest. You drive your car, but it eventually stops. So what in the world? Is Sir Isaac Newton right? Well, it turns out that Newton's first law, describing an object in motion staying in motion, is true when there's no other forces. But all around us, there's the force of friction, which tends to slow things down. And that's just what we'll study in this lesson. Let's take a look. Let's start by considering our lesson objectives. First, we'll understand friction's impact on motion. Hint, it slows things down. Then we'll solve qualitative problems with friction and Newton's first law. That means problems using words instead of numbers. But then we'll move on to numbers and solve quantitative problems with friction and Newton's first law. Let's remind ourselves of what Newton's first law says for objects in motion. It says that an object will move at a constant velocity unless a net external force is present. Wow, that's a lot. We usually summarize this as an object in motion will stay in motion. But of course, that's not what we always observe. Generally speaking, we actually observe things to slow down. It's the reason we think of objects as naturally coming to rest. We create acceleration with a force and then slowly, friction from, in this case, a pool table, and the air brings it all to rest. Let's take a closer look at friction and consider its impact on motion. What is friction? It's a resistance to motion. So if you're pushing on something, or if something's in motion, friction slows it down or keeps you from being able to move it. Consider sanding. The rough surface of the sandpaper rubs against the rough surface of the wood. These two surfaces create friction. It's hard to push that sandpaper back and forth because of the rough, jagged edges. These jagged surfaces at this scale and even at smaller scales cause friction. But of course, friction isn't just caused by surfaces. It can be caused by air also. That's why this parachute drops slowly. Air molecules collide with the big surface and slow down your fall. In both these cases, friction is caused by matter that is in contact with an object, either air or rough, small surfaces. Friction is caused by matter in contact with the object. Friction is caused by matter in contact with the object. So when there isn't any matter, for example, in the depths of space, things just continue to drift, and there isn't any friction. There's no resistance to motion. Here we see very neatly Newton's first law, that an object in motion stays in motion. Now let's consider objects as they either stay at a constant speed, slow down, or speed up. An object at constant speed is like this skateboard. It's moving forward at a relatively constant speed, despite the fact that it's in contact with the surface of the ground and with air, which would cause friction. Why does the speed stay constant? Oh, well, it's because every single time it would slow down, the skateboarder pushes off with their foot. And this teaches us something important about friction and things at constant speed. For an object at constant speed, we can say that the applied force is equal and opposite of friction. So the foot pushing forward is equal to the friction that's pushing back. We can summarize this way. The applied force is equal to friction. Now, this statement doesn't include anything about the opposite part, and so that's why we have to use those strange vertical lines. Those vertical lines indicate magnitude. Let's go on a brief interlude to talk about magnitude, and then we'll come back to our lesson on friction. When we use those vertical lines, we just mean magnitude of a vector. Let me give you an example. If I take a look at this vector, the force of friction is equal to 155 newtons northwest. What is the direction portion of that vector? Well, the northwest. Okay, what's the magnitude portion of that vector? Okay, well, the magnitude is just like the size, and it would be 155 newtons here. So we can summarize that by using these vertical lines and say that the magnitude of the force of friction is 155 newtons. Okay, where were we? That's right, we were talking about objects changing speed. What about an object speeding up? What can we say about friction there? Here, this motorized paraglider speeds up. The fan pushes air backwards and accelerates it. But it runs into other air molecules that would slow it down. How does the force of friction compare to the force from the fan? Well, you guessed it. The force from the fan must be greater than the force of friction. For an object speeding up, the magnitude of the applied force, in this case the fan, but it could be an engine or a push or a pull, has to be greater than friction. So for an object to speed up, the applied force must be greater than friction. What about for an object slowing down? Well, here we see those pool balls, again, slowing down. How do you think the force of friction relates to the applied force? That's right, the applied force must be less than friction. And that's kind of obvious here, because after the pool player strikes the cue ball, there's no force being applied at all, just friction. And so the object slows down. So for an object slowing down, the applied force must be less than friction. For an object slowing down, the applied force must be less than friction. Let's look at an example. A father pulls his children with a force of 200 newtons. If the force of friction is 150 newtons, what happens to the velocity of the wagon? Well, let's start by just making a free body diagram to think about the forces. Here's the pulling force. So the father's pulling the children. That one's about 200 newtons. Okay, which direction will the friction point? Think about that for a second. Yeah, it's going to point backwards. It's resisting motion. And so friction will point backwards. Notice that the force pulling forward is greater than the force of friction. So here we have a case where the applied force is greater than the force of friction. What does that mean? That means it speeds up, or we say accelerates. So the velocity of the wagon increases in this case. All right, let's look at another example and identify some forces of friction. What are the two sources of friction on this box? As the father pushes his daughter forward, the ground actually pushes back. So there's friction from the floor. What else? Well, as the daughter is pushed along, air molecules collide with her and the box and slow it down. So friction also comes from the air. Okay, if a father pushes his child at a constant velocity with a force of 80 newtons, what is the magnitude of the force of friction? The trick here is to remember that the velocity is constant. If the velocity is not changing, then the magnitude of the applied force and the force of friction are the same. So the force of friction must be exactly 80 newtons. One more question about this circumstance. What is the direction of that force of friction? Well, it must be backwards towards the father because friction always opposes motion. Okay, now let's move on to a quantitative problem where we'll actually solve for a numerical value for a force of friction. A father pushes his child at a constant velocity with a force of 80 newtons. If the friction from the air is 20 newtons, what is the friction from the ground? Well, we can start with this very important equation. At constant velocity, the force of friction is equal to the applied force. This is a very important starting point for any constant velocity problem with friction. We know that the friction and applied force are the same. In this case, the friction comes from two things, the air and the ground. So we can split that up and say that the force of friction from the air plus the force of friction from the ground is equal to the applied force. And we know the force from friction from the air is 20 newtons and that the applied force is 80 newtons. So substituting those in leaves us with just one unknown, the force of friction from the ground. Now we need to subtract 20 newtons from both sides to get the force from friction from the ground by itself. 20 newtons minus 20 newtons cancels out and goes to 0. 80 newtons minus 20 gives us 60. And so the force of friction from the ground is 60 newtons. Okay, let's do one more quantitative problem. This one says that a plane with 4 propellers flies at a constant velocity. And then it tells us that if each propeller provides a thrust of 2,500 newtons, what is the magnitude of friction due to the air? Well, again, we start at the same place by reminding ourselves that the force of friction is equal to the applied force. Those magnitudes are exactly the same. Why? Because we're moving at constant velocity. That's the key. Okay, so remember that the applied force comes from our propellers. How many propellers do we have? 4 of them. So we can substitute in 4 times the thrust from each propeller. So the force of friction is equal to the applied force, which we know is equal to 4 times the force from each propeller. Now, we know each propeller has a force of 2,500 newtons, so the force of friction must be equal to 4 times 2,500. And then we just multiply that through, and we get that the force of friction in this case is 10,000 newtons. Let's summarize what we've learned. First, we understood friction's impact on motion, basically that it slowed things down. We learned that for motion at constant velocity, the force of friction is equal to the applied force. Then we solved some qualitative problems with friction and Newton's first law, where we took a look at the direction and magnitude of friction for things moving at constant velocity. Lastly, we solved quantitative problems using numbers with friction and Newton's first law.
Hey, hey.